Hello friends, welcome to Make and Link. Today we are going to start 5th lecture of design of reinforced concrete structure. This lecture is on design of singly reinforced beam based on working stress method. In the 4th lecture, I explain you about the working stress method in detail with examples on analysis. So before watching this video, I would recommend you to watch the previous lecture in case you have not seen them, so that you can easily establish a link between your analysis and design concept. There are two parts of this lecture. First, I will show you the design concept of working stress method with procedure of designing. Whereas in the second part, we will study an example of design of beam section. So let's start here with first part. In previous lecture, I have explained you about three types of beam section based on relative quantity of concrete and steel used in beam. The sections are under reinforced section, balanced section and over reinforced section. In practice, it is always advisable to design as an under reinforced or balanced section because in these sections there will be a clear warning of failure in the form of large deflection and well distributed cracks with a smaller quantity of steel. Under reinforced section fails due to failure of steel. That's why we call it ductile failure. Here you can see the failure pattern of under reinforced section. Here the cracks are large and visible before failure of beam section. On the other hand, over reinforced section are not preferred since they require large quantity of steel, and under overloads members fail suddenly with explosive failure and negligible deflection and very few cracks. The reason of sudden failure is concrete brittleness. We know that concrete is a brittle material, hence this failure is also known as brittle failure. You can see here the failure pattern of over reinforced section. Now let me show you the design procedure of singly reinforced beam. In third lecture, I have explained you about analysis versus design. In design problem, design load and moment are already given, and most of the time grade of concrete and types of steel are also given. You have to find out the cross-section dimension of beam section and how much steel is required. So design steps are: the first step, write the given data. In most of the question, the effective span, loads and grade of concrete and types of steel are already given. In the second step, you have to write down the design constant like modular ratio, permissible stresses of steel and concrete. Depending on the type of examination, the value of permissible stresses may be given or not, but it is always advisable to note it down from IS code table number 21 and 22. Next is find the critical axis coefficient, lever arm coefficient J and moment of resistance coefficient Q. After that, third step is for designing. You have to find out the cross-section dimension of beam you are going to design, which is very important step in designing. Initially assume the overall depth, we can call it D provided as 1/10 of effective span. Next we have to calculate the required depth, which is the combination of effective depth and effective cover. First look on effective cover. If you recall from first lecture under the topic of durability of concrete, we learned the concept of nominal cover. We use nominal cover to protect the steel from corrosion, but here we are designing a singly reinforced beam, so let me illustrate it on singly reinforced beam. Effective cover is nominal cover plus half of bar diameter because we measure it from centroid of steel. Later we modify this formula when we use the stirrup for shear and torsional strength of beam. Next important step is to how to find the effective depth. As I have told you earlier that it is advisable to design a beam as under reinforced or balanced section. Under reinforced section means that moment of resistance is more than the applied moment. On the other hand, the balanced section where moment of resistance is exactly equal to applied moment. In last lecture, I have derived the formula for moment of resistance for balanced section. That moment of resistance is equal to QBD square. So the formula for effective depth for under reinforced section will be D is greater than under root bending moment upon QB. For balanced section, D is equal to under root bending moment upon QB or under root moment of resistance for balanced section upon QB. Here you can see from this formula that we have already calculated the value of Q. Now we calculate the bending moment and breadth of beam. So to calculate bending moment, you must first calculate the total loads on the beam, including the self weight of beam. So the self weight of beam per meter will be gamma BD kilonewton per MQ. Here self weight also depends on breadth of beam section. Hence next important step is, if the value of breadth is not given in question, then how to find the breadth of beam section. The first rule is span upon 30 plus 8, where the units are in centimeter, which can be converted into meter or millimeter. There are some thumb rules to find out the breadth of beam section. You can use the width of column on which beam is going to rest as the breadth of beam section, or width of masonry wall which is going to be supported on beam. If all the above given sections are not possible, then you can assume it between 250 mm to 300 mm. So after finding the breadth of beam section, it will be easier to find the self weight of beam section. You might here think that what will be the value of unit weight gamma for concrete. So the value of gamma are, it will be 25 kilonewton per m cube for reinforced cement concrete, and it will be 24 kilonewton per m cube for plain cement concrete. After finding the bending moment and using the value in the formula, find out the effective depth. Here you have to check the value of effective depth according to IS code provision. Minimum effective depth D is span upon 20 for simply supported beam, span upon 7 for cantilever beam, and span upon 26 for continuous beam. Now you have calculated the effective depth as well as effective cover. Summation of both values give us the D required. The important step here is to check that D required should be less than D provided. If D required is not less than the D provided, in this case you must revise the process by assuming the D provided larger than the previous one. After this step of finding the cross-section dimension, the final step is finding the area of steel we use in tension zone. Here we know the formula of moment of resistance from tension side. It is sigma st into ast into d minus xa upon 3. We can further modify it as sigma st into ast into jd. So to find out the area of steel, the formula is ast is equal to moment of resistance upon sigma st jd, or we can also use bending moment, because for balanced section moment of resistance and bending moment both are equal. So it will be bending moment upon sigma st jd. So here we have find out the area of steel, but we know it very well that steels are available in market in the form of bars of different diameter. So we have to convert this area of steel into number of bars. First you have to assume the die of tension bar. The options are available with us are 12 mm, 16 mm, 20 mm and 25 mm. After selecting the proper die of bar, you can calculate the number of bars. So the formula is area of total steel AST upon area of 1 bar. Now the final step is to check it for minimum steel. If you are designing RCC beam, then you have to provide minimum steel as per IS code provision. AST minimum upon BD is equal to 0.87 upon FY. So the minimum steel will be 0.87 BD upon Fy. If it is not satisfied, then you have to revise the design process with more steel. But keep in mind your design should be either under reinforced section or balanced section. So here we have finished the concept of designing a singly reinforced beam according to work stress method. I hope you are clear about the design process, and we can move on to the next part where we will be designing the actual beam section in different numerical problems. Here is example number 3 of this lecture series. The question is, a rectangular beam with 400 mm is to be designed for a live load of 30 kN per meter, excluding the self weight of simply supported span of 7.5 meter. The question is, design the beam if M20 grade of concrete and Fe 500 steel are used. So the strategy for question, write down all the given data and design constant, then find out the cross section dimension and area of steel using design step. So the solution is, the first step is write the given data. The first one is effective span, which is already given as 7.5 meter, and we can convert it into 7500 mm. The breadth of beam 400 mm. Applied live loads 30 kN per meter. The grade of concrete is M20, hence the characteristic strength FCK will be 20 Newton per mm square, and yield strength of steel is Fy 500 Newton per mm square. So the second step is write the design constant. The modular ratio for M20 grade of concrete is 13. The permissible stresses in concrete is sigma CBC 7 Newton per mm square, and for steel sigma ST 275 Newton per mm square. Next is critical neutral axis coefficient Kc, and we know the formula of Kc as 1 upon 1 plus sigma st upon m sigma cbc. Here put all the value of sigma st and sigma cbc, and the final value is 0.248. Next was the lever arm coefficient, and the formula is 1 minus Kc upon 3. We have already calculated the value of Kc. It will be 1 minus 0.428 upon 3. The value of J is 0.917. Next design constant is moment of resistance coefficient Q, and its formula we know already, 1 by 2 sigma CBC Kc into J, and we already calculated the value of Kc and J, so the value will be 1 by 2 7 into 0.248 into 0.917, and the final value of Q is 0.80. The next important step is find the cross section dimension. As I have told you in design step that first we have to assume the D provided as 1/10 of effective span, and it will be 7500 upon 10, and the value will be 750 mm. Next step is self weight of beam, and we know its formula gamma BD. Here we are designing the reinforced beam, and the value of gamma will be 25 kN per m cube, and the value of B convert into meter 0.4 meter, and value of D overall depth 0.75 meter. Hence the total self weight of beam per meter is 7.5 kN per meter, and the total load will be live load plus self weight of beam, and the value of live load is 30 kN per meter, and total load will be 30 plus 7.5, 37.5 kN per meter, and the maximum bending moment for simply supported beam will be WL square upon 8, where W is 37.5 and effective span 7.5 square upon 8, and the final bending moment value is 263.67 kN meter. We can calculate the value of effective depth with D is greater than under root bending moment upon QB. When we put all the value here, 263.67 into 10 to the power upon 0.80 into 400, the value of D is greater than 906.67 6 mm. So the value of D required, the required depth of beam will be effective depth plus effective cover. Let us assume here the effective cover as initially let us assume as 50 mm, and the final value will be 956.6 mm, which is greater than D provided. We know that the value of D provided 750 mm, so we have to redesign the depth. Our concept is that D required should be less than D provided. So let's try the second trial. Assume D provided as 1000 mm. So we have to calculate the self weight of beam again because we have changed the cross section dimension of beam. So it will be 25 kN per MQ into 0.4 meter into 1 meter. We have changed it from 750 mm to 1000 mm. So the self weight of beam will be 10 kN per meter and the total load will be 30 kilonewton per meter live load plus 10, it will be 40 kilonewton per meter, and then again the maximum bending moment will be 281.25 kilonewton meter. Again we put this value into the formula D greater than under root bending moment upon QB. So the value is 281.25 into 10 to the power 6 Newton per mm upon 0.80 into 400 mm. Here the value of effective depth is greater than 936.33 mm. Let us assume it in round figure 940 mm. Here either you can use the effective cover as a 50 mm or we can calculate it as I have explained you the concept in design step that effective cover is nominal cover plus bar dia upon 2. And for simply supported beam, most of the time the nominal cover is 25 mm, and let us assume that we are using 20 mm dia bar in tension zone. So it will be 25 plus 20 upon 2, 35 mm effective cover. And the final value of D required will be 940 plus 35, 975 mm, which is less than 1000 mm. So we have satisfied the first requirement that D required is less than D provided. The next step is find the area of steel, and we know the formula is area of steel is equal to bending moment upon sigma st jd. Here bending moment is 281.25 into 10 to the power 6 upon the value of sigma st permissible stresses for steel is 275, value of J is 0.917 and value of effective depth is 940 mm. So when you solve all these values, it will be 1186.47 mm square. So this is the area of steel. Now we have to find out the numbers of bar we use for steel. We have already assumed that we are using 20 mm dia bar. So the numbers of bar will be area of steel, overall area of steel AST upon area of 1 bar. So it will be 1186.47 upon pi by 4 into 20 square, the area of 1 bar, and the value is approximate 3.7. So we will assume that we are using 4 bars of 20 mm dia, and the final area of 4 bars of 20 mm dia is 1256 mm square. The next step is we have to check for the minimum steel according to IS code provision, and the formula is we know that AST minimum upon BD is equal to 0.87 upon Fy. So we can modify this formula into another form. Minimum area of steel is equal to 0.87 BD upon Fy, and put here the value 0.87 Fy into value of B 400 into D 940 mm upon yield strength of steel 500 Newton per mm square, and the minimum area of steel is 654.24 mm square, which is already less than 1256 mm square, and it is satisfy the criteria which is required by IS code. So here we have designed the beam section with 400 brush already given. So here we will use 4 bar of 20 mm diameter and with effective cover of 35 mm and effective depth 940 mm. and the overall depth of the beam section will be 975 mm. So here we have finished the first lecture. Let us summarize it. Initially, I explained you the concept of design according to working stress method, where I told you that we design beam always as either under reinforced or a balanced section. Then I explained some steps for designing, and finally a practical example for design of singly reinforced beam. So here we have finished the working stress method. Despite the fact that working stress method has a lot of drawbacks and is no longer in use, we considered it important to introduce you to this method also. But from now onward, we will be studying only limit state design and their application to problems in upcoming lectures. If you have any query, please comment below so that we can get back to you shortly. Thanks for watching. Team Macon Link.